Alrighty, so we are starting a new unit here in algebra about functions. Just a reminder for you about functions. This graph right here on this t-shirt is a function called a parabola or a quadratic. We're going to look at functions like that. But in case you need a reminder, functions are equations and graphs and tables where each x value has only one y value. Okay, so that's our really key thing, is that unlike in, let's see a graph. Sometimes we would have a graph that looks like this curvy line. That would not be a function, because when you are at the x value 0, there are multiple different y values that you could have. So that is not a function. A function would be something where for where we are on the x-axis, we have only one y value or one output. Okay, so there's a reminder for functions. A parent function is the most simple form of an equation. Okay, so a parent function is kind of like if you think about a parent being the one that comes first, right? The parent comes before the kid. You have to have a parent before you can be for a kid to exist, right? So the parent function is the one that comes first, and it is the most simple form. So everything else is a variation of it, but it all comes back to what does that parent look like, and we'll show some examples of that in a second. Parent functions include x and y and their required operations, but no other variables, which means that it might have x equals y. We might have y equals x squared, because that squared is that operation. It's an action that's happening to x, so we can still have that, but we're not going to have any other variables, any other letters involved. And lastly, parent functions always pass through the point 0, 0, which is often the point of symmetry. Oftentimes that's where we're cutting our graph in half, is through that point 0, 0. Okay, so those are some key takeaways about parent functions. Some of you might have have done this before, and if not, that's okay. We're going to look at the graph that's called a linear parent function. So if you look right here, the parent function is the linear graph. If I look at that graph, we can see it looks like a line. And then if I put in my non-parent function version, so this version here, y is equal to ax plus k, okay? If I move around what these values are, I can change what that graph is, okay? But eventually, it's going to be just like our parent function. So I can set it to be like our parent function. See right here, it matches, but then as I change these different values, it's going to change the graph. But no matter what, it's still a line, right? It's just changing how stretched down it is or how far up and down it goes, okay? So we're going to focus in on linear graphs first. Linear graphs and functions are, the parent function is written as y equals x, which means whatever the y value is, the x, or whatever the x value is, the y value is going to be the same. So if I draw a table, if I have -2 as an x value, well, -2, I lost my pen there for a second. I got y equals -2. Well, that just means that y equals -2. When x is -1, y is -1, x is 0, y is 0. And it continues into the positive range. So when I plot this on my graph, I got my point at 0, 0, my point at -1, -1, -2, -2, -3, -3, 1, 1, 2, 2, 3, 3, 4, 4, okay? And then I can draw my line connecting through them. In both directions, and I apologize for how that line isn't super accurate, but right, we want a nice straight line going through all those points, okay? And some key points to note, we always go through that point 0, 0. When we're up in this range, right, I have a +4, +4. When I'm down in my negative values, I have -4, -4. Okay, so those are some key points to point out, that it's always the same number and the same sign. Now, sometimes we modify or we change our linear function. And so our transformed function is going to be y is equal to mx plus b. This might look familiar to you. You might have done some work finding the slope or the x-intercept. But what our transformed version does is it changes the steepness or the slope and the height. So those two pieces are going to change the steepness and the slope and the height, but everything else is going to stay the same. Okay. The next kind of graph that we are going to look at is a quadratic graph, and this might also be familiar to you. When I turn on my quadratic function, I have this nice parabola or this nice U shape, okay? And this U shape, we're going to, if I turn on my modified version, I can see again that I'm changing how wide it is, if it's facing up or down, but it's still always looking like a U. And I can change how side to side it goes, and I can change the K value or the height, okay? So when I look at quadratics, okay, for my quadratic, I want purple, my parent function is y is equal to x squared. Okay, that is my parent function. And what that means is that when I make my table, my y output is always going to be x squared. So if I have a -2 for x, -2 going in for x squared is +4. -1 would be 1. 0 would be 0. 1 would be 1. And +2 would be +4. So notice how here I only have positive outputs for positive y values. Okay, that's kind of a big piece of it. When I plot these, I always am going through that 0, 0. I got my 1, 1, and my -1, 1. And then I got my 2, 4, and my -2, 4. I'm going to make sure to write those down as some key points. Showing how my output is the same even though my x value is different. And I have my nice U shape. That is not a nice U shape. Let's try to make it a little better. Oops. Okay, there we go. Now sometimes we can transform our quadratic, or we have a transformed version. Okay, and our transformed version might look familiar to you. It is y is equal to a x minus h squared plus k. Here's my minus sign. Okay. And what we noticed when we looked at the graph just now is that when I change my h value, I'm not changing the shape at all. When I change my k value, I'm not changing the shape, I'm just moving where it's at. The only thing that changes my shape is my a value. And what it's going to do is it's going to say my values are either going to be really, really close together, my y values, sorry, where you see how I go, I got this nice point here at like 5, 3.5 almost. And then at 6, I'm at 5 exact, right? So I'm getting really close, or 3.5 to 5, right? Or my values aren't changing a whole lot on the y value when I change my x value. Whereas if I make my a value, really, really big, between each point we go from having our low point here to jumping all the way up to our next nice point. So in the course of one value, my height changes by a whole lot, okay? And so what we're gonna note with this is that our vertex, or our lower high point, will shift up or down and side to side. And other values will stretch or shrink. Okay, these values are going to jump by bigger amounts. Okay, the next kind of parent function that we have is the absolute value graph. And I like absolute value graphs because it's a combination of the last two graphs that we talked about. So if you look at our absolute value graph here, y is equal to the absolute value of x, we see that if I just look at this upper corner, it looks like our linear graph. And if we look at the other side of it, it looks like our linear graph but upside down. So our absolute value graph is very, very similar. It just only goes up. And we see it kind of makes the similar shape as the quadratic. Now, in case you forgot, and that's okay, absolute value means the distance from 0. Meaning that if I have, and I'll write our parent function is y is equal to the absolute value of x. So if I have my table here, if I put in a -2 for x, how far away is -2 from 0? Well, it's 2 away from 0. It doesn't matter that it's negative or positive. It's still going to be 2 away from 0. Same thing goes with -1. How far away is it? Well, it's 1 away from 0. How far is 0 from 0? Well, it's 0. How far is 1 from 0? 1. And 2 is 2. So very, very similar values to what we had with our linear graph, except we only have positive output values, okay? So we're kind of taking these two. Our quadratics also only had positive output values. And our linear graph had the same value for x as y when we're in our positive numbers, okay? So it's kind of a combination of both. Now our transformed version is going to act the same way that our quadratic transformed version did. So we're going to have y is equal to a, absolute value, x minus h plus k. So see, we keep our absolute value of x part, we just added in a little negative h or minus h in there. And it's gonna do the same thing. So when I turn on my absolute value modified version and I go to change my a value, you'll see it changes how steep it is. So sometimes it's really, really skinny and we're moving a lot between each x value. Sometimes it takes a long time to get from an x value or one y value to the next, okay? It took about 3 whole numbers to just move up 1, okay? So, same idea. Our vertex moves. So that low point is going to move. Lower high point is going to move. And values will be bigger. Gaps between each output will be bigger or smaller, I should say. Okay, those gaps are going to change. We're going to be moving faster or slower up the line. Our next graph that we're going to look at is called the square root graph. And square root graphs are probably the most unique of the ones we're going to cover. Square root graphs we notice just right off the bat, looking at it, does not have anything on the right side, or left side, sorry. We only have stuff on the right side. And if you were to type into your calculator, to take the square root, let's get my square root sign out here, square root of -3, it will say unidentified. And what that means is that we cannot take the square root of negative numbers. So the first value we can look at is 0, 0. Okay? So when I look at my square root, my parent function is going to be written as y is equal to the square root of x. Okay? And then I'm going to take that and my x value, y value table tells me I have to start at 0, 0. If I take the square root of 1, I get 1. If I take the square root of 2, let's get our graph back here, or my calculator back here. If I take the square root of 2, I get a weird decimal. I don't really want to write that out. If I take the square root of 3, I get another weird decimal. I'm going to keep going until I get a nice number. And if I take the square root of 4, I get 2. So I'm going to use that instead because that seems much, much easier. So the square root of 4 is 2. The next nice number we get is 9, and the square root of 9 is 3. So you'll notice that my y values grow really, really slow. Okay? They're only incrementing by 1 each time. Whereas my x values are growing really fast. We go from 4 to 9. We're skipping around. So when I plot my points, 4, I believe this would be 9. I have 0, 0, 1, 1, 4, 2, 9, 3, okay, making an arced shape along the graph. Now when we modify this graph, you'll see that we can start to go into the negative zone a little bit. We can start to move side to side just a little bit, moving my h value side to side. I can go up and down, and I can even turn itself upside down. Okay? I can be almost so straight that it's like not even, or more of a rainbow, or I can flatten it out so it's more like a line. I can flip it upside down. Okay, lots and lots of different ways that I can change the stretch of it. So we find that our transformed version of our function is y is equal to a square root x minus h, and then on the outside we add k. Very similar to what we've done. The vertex, or in this case our low point, or our end point, moves, and other points stretch, shrink, or flip. Okay, so that's what happens. We can have a nice flipped graph. We could have a nice tall graph. Okay, lots and lots of different ways in which the square root graph can change. Our final form is called a cubic, and cubics are kind of like a combination of the last couple graphs as well. So if I look at my cubic functions, the cubic function parent graph, we'll zoom it in, makes a nice squiggle, okay? And what you'll notice is it goes up, 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 kind of flattens out just a little bit, and then it keeps going up, but it faces the other way. So this is like a rainbow, and this is like a U. And it kind of sort of looks like a parabola that's been cut in half and changed, and flipped. The difference is that although we have this point 1, 1 like we did, at 2, instead of being at 4, which we've been at in the past on 2, When we are at an x value of 2, we are all the way up at 8. Let's see if it'll show it. Okay, so we're going to grow much, much faster. So our parent function for a cubic is y is equal to x cubed, or x to the third power. So instead of squaring values, we're going to take them to the third power. Now, if I put in -2, this is saying -2 times -2 times -2, because that's cubing, is multiplying it by itself 3 times. Well, -2 times -2 is 4, times -2 is going to get me -8. So I have -8. If I put in -1 times -1 times -1, I'm going to get -1. 0 is going to get me 0. 1 is going to get me 1, because now we're in the positive zone. 2 is going to be 2 times 2 times 2. Gets me 4 times 2, which equals 8. So you'll see I'm bouncing really far between each of these values. I go from -8 to -1, okay? And I can have a negative value now again for a y output. I'm not stuck in the positive land. So I'm going to put my point at negative, is that 4? It might be. Here we go. -8, 1, 1, or -1, -1, 0, 0, 1, 1. I think that's 8. 2, 8. So now we get to have both sides represented a little bit more. We get negative numbers and positive numbers. -2, -8. Okay, so there is my cubic parent function. When we want to look at the transformed function now, I can see that I can shift my graph to be upside down, to be flatter, to be skinnier, okay, to move side to side, and to move up and down. But all along, it's still keeping the shape of being a quadratic or a cubic. It's just changing how cubic it looks, okay, or how stretched or skinny. So my transformed function and maybe you've caught on to this, is going to be a x minus h cubed plus k. So we always have this a, this h, and this k happening, and we're going to talk later about what each of those pieces do. But we know that the turning point will move, and the other values stretch, shrink, or flip. Okay, so that we can have graphs that are upside down, okay, that we can have graphs that look way more flat, or that look way skinnier, okay? So lots of different changes that we can make. I would say cubic is the most fun to switch our a value back and forth on, because if I do it really fast, it looks like some arms on a guy that's dancing, and he's waving his arms up and down and up and down and up and down. And who doesn't love to have a dance party in math? So these are our 5 different parent functions, okay? To summarize them up, they are our linear is y is equal to x. Quadratic is y is equal to x squared. And our linear is a nice straight line. Our quadratic makes a u. Our absolute value is y equals absolute value of x, which makes a nice V shape. Our square root is y is equal to the square root of x, which is a nice arc. And finally, our cubic, where y is equal to x cubed, and we got dance and arms. Okay. So these are our parent functions. We modify them or transform them to get different kinds of lines that fit different situations and represent different relationships between values, but they all come back to these parent functions.